In this example, we're going to look at comparing different types of functions. So we have the graph shows population models for 3 cities based on data over a 5-year period. So we can see we've got city A has this f of x function, 3.2x. That is linear. We can see it's a straight line. City B is g of x equals 0.25x squared. So that is quadratic. You can see it's increasing, looks like kind of part of a parabola right here. City C, h of x equals 2 raised to the x minus 5 power. This one is exponential, so it's kind of slowly increasing, and then that increase, it's going to start to increase at a faster rate. That's how exponential functions work. So if the population continues to increase in the same ways, when will the population of city C, that's our exponential right here, exceed the populations of the other 2 cities? So visually, from the snapshot that we have right here, we can see that this has the lowest population. These the population is our y coordinate. All of these graphs are essentially above this one. But at some point, when is this going to take a turn and go whoop and increase beyond the other ones? So we've got a couple methods to do that. Our first one is to use a table of values. So here's a table of values for all 3 functions. We've got our x coordinates, and then these are the y values of f of x. This is city A, the linear. Here are the y values of g of x. This is city B, the quadratic function. And these are the y values of h of x, city C, which is the exponential function. And they want us to compare when city C, so we're looking at here's city C, when does this exceed the population of the other 2 cities? So you notice we have really low population, right? I guess we're in millions, like 4 million, 8 million, but that's compared to 16 million in city B, 25 million in city A. So at what point does this get bigger? So we're getting closer at 32. 32 is bigger than 25, so we have exceeded city B, but it's the same as city A at 32. But here, after 10 years, and before we get to 11 years, at some point in that range, city C has exceeded. We have a higher population in city C than the other 2 cities. So we can say that after year 10, we don't have the specific data to know was it 10 years in a month, 10 years in 3 months. So we just say after year 10, we know it happened after year 10 at some point. The population of city C is greater than those of cities A and B. Okay, another method is to use a graphing calculator and determine the points of intersection to see when one function exceeds another function or gets greater than another function. So here is our linear city A. Here is our quadratic city B. And then here is our exponential function city C. So it's the same functions we had up above, but if we just look at a different snapshot, we see more of the cities. We can see that right here. So this function is less than the other functions. At this point, the population has increased and gotten higher than the population of city B. And here's the point after this is when the population is greater than, as our x's continue, as we move out in number of years, after this mark, which is that ordered pair, that's what this tells us down here, that's 10, 32. So after year 10, city C will have a population that exceeds, it will now be greater than the other 2 populations. And then I just want to point out that because city C is exponential, it is going to exponentially grow. From here on out, after year 10, it's always going to have a higher population than the other two cities. The linear and the quadratic function won't come back and increase higher than this one. So it's because it's exponential that is happening. So just good to know. All right, so now that we kind of see what we're doing, let's try one on our own. Compare functions f of x, which is linear, 3x plus 2, with g of x, which is quadratic, it has an x squared, 2x squared plus 3, with h of x, 2 to the x power, which is exponential. Show that as x increases, h of x will eventually exceed f of x and g of x. So I'm going to show you how to do this on your graphing calculator. All right, so we're going to compare three different functions. We can do that with our graphing calculator by going into our y equals and typing in our three functions. So I've already done that. y1 is our f of x, 3x plus 2. That's an x to the first power. That's going to be a linear function, just a straight line. y2 is our g of x function, 2x squared plus 3. Because of the x squared, that will be quadratic. It will have a parabola-shaped graph. And then y3 is our h of x, that is equals 2 to the x power. This is exponential function. So what we're asked to determine or just show that as x increases, h of x will eventually exceed f of x and g of x. So we're looking to see when h of x down here will eventually exceed these two. We can do this two ways if we compare table of values. So I'm going to hit second and graph so I can get to that table option. What's nice here is we see the x values and then we see the y values for our three different functions, and we can just compare our y values. So when x is a negative 11, we can see we have a negative 31 for our linear function, a 245 for our quadratic, and this 4.9e negative 4, that's scientific notation. We would move that decimal 4 spots to the left because of that negative 4, and we have a very small decimal. What we're looking for, this y3, that was our h of x function. We want to show that this function will eventually exceed the other two. So we're looking to see when the y values get bigger than the y values of the other two functions. Right now, down here at negative 1, we're not there yet. So we just scroll through our table and we pay attention to, all right, we're at 5, 5, 2, we're still smaller down here. 4, still smaller. We just kind of keep going until we notice that this y value is exceeding these y values. So right now, our exponential function has exceeded our linear function because this 16 is bigger than the 14. So at this point, this function is greater, but the question is to show when it's greater or when it has exceeded both. So we keep going until we see that this number is bigger than both of these. So it's going to be bigger than the linear function the rest of the way. So now we're comparing to the red one, the quadratic. We keep going, and here's where we can see that it got bigger. So our exponential function, the h of x equals 2 to the x power is 128. That is now bigger than the 101 and the 23. So that happened sometime between 6 and 7. So when our x value was greater than 6, this one right here, at some point that's when we exceeded, when the h of x exceeded the other two. So you can see in a table of values how to look for that. If I come back and I graph the functions, here's what they look like graphed. So the blue line is our f of x, that's our linear function straight line. The red, this is a parabola, kind of a wide parabola here. Well, actually, it's more narrow than the parent function, but it looks a little bit off because of our axis here. And then this black function right here, this is our h of x, our exponential. So you can see as we move along, maybe I'll actually trace that one. I'm going to hit trace. I am tracing the blue function, so I'm going to arrow down. Now I'm tracing the red function. I'm going to go down one more time. Now we're tracing, there's that exponential function. So I'm going to hit over. You can see we are less than the other two functions. And I keep going, we're still less than the red parabola. Right about here, where they seem to intersect, that's when it switches. Now, as the x's increase, and actually we can see that happens at about a 6.36, but as I continue to the right, as the x's get bigger, now our this function is greater than the other two. And it will continue to be greater than the other two because it is exponential.